Are you planning to design a system that uses OBI to connect an accelerator to a RISC-V core? Perhaps you are designing a memory controller or a peripheral that needs to be OBI compliant, and you are not sure where to start. If so, you are in the right place. In this video, I'll walk you through how to design an OBI master and a slave from scratch. We will then verify them using the OBI test suite from the PULP platform, a popular open source RISC-V system. All the code and the complete simulation environment are available on our GitHub repository. You can find the link in the video description below. Here's a look at our agenda for this video. First, I explain what OBI is and cover the fundamental transaction phases, including read and write operations. Then, I'll dive into signal dependencies, which are critical for avoiding combinational loops when generating requests and responses. After covering the theory, we'll move to the practical part. We'll design an OBI master to control a memory module. So, what exactly is OBI? OBI stands for Open Bus Interface. It's a simple, synchronous, and pipeline bus protocol designed for high performance yet low complexity communication between IP cores. Key features include separate channels for requests and responses, and it operates as a handshake base or request grant protocol. The protocol works in two main phases, the request phase and the response phase. In the request phase, the master initiates a transaction and the slave accepts it. In the response phase, the slave signals back that either the requested read data is ready or that the write operation has been completed. OBI signals. For this tutorial, I'm referencing the OBI version 1.6 specification. A link to the document is available in the description. This table lists the required signal. Let's go through them one by one. CLK or clock. Since OBI is a synchronous interface, all masters and slaves share a single clock. Reset signal. This is an active low reset. When this signal is low, the modules are held in a reset state. REC. Driven by master, this signal initiates a transaction. GNT. The grant signal, driven by a slave. It indicates that the slave is ready to accept the request. ADDR, the address bus, driven by master. The write enable signal, driven by master. When it's low, it indicates a read operation. When high, it indicates a write. W data, the write data bus, driven by a slave. BE, the byte enable, driven by the master. This indicates which specific bytes on the data bus are valid for the transaction. Are valid, driven by the slave. This signal confirms that the read data is available and valid on the R data bus, or that a write operation has been completed. R data, the read data bus, driven by the slave. The default address and data bits are both 32 bits. OBI transaction phases, read operation. Now let's look at the read operation, which happens in two phases. First, address or request phase. The master begins by setting up the transaction. It drives write enable low to indicate a read. It places the desired address on the address bus. It sets the byte enable signal as needed. Finally, it asserts request high to initiate the read. When the slave is ready, it asserts grant high to acknowledge the request. Once the master sees the grant signal, it knows the request was accepted. At this point, it can either start a new transaction or end the communication by deasserting the request. Second, response phase. The slave processes the read request. When data is ready, it places the data on the R data bus. Then it asserts R valid high for one clock cycle. The master then captures the R data on the clock edge, where R data is high. OBI transaction phases write operation. The write operation is similar to read operation, with the key differences being that the write enabled signal is high, the master places data on W data, and the master doesn't wait for the R valid signal. As demonstrated here, you can see that the master sets its request to high, and in the same clock cycle, the slave acknowledges the request. After some clock cycles, the slave sets R valid to high to indicate that the write operation is complete. OBI signal dependency. To avoid deadlocks and combinational loops, it's very important to pay attention to signal dependency. Master interface restrictions. For the master interface, it's critical that the request outputs do not combinationally depend on the grant or R valid inputs. Do not generate a request directly from grant or R valid. This helps prevent circular dependencies that can lead to unexpected behavior. A slave interface restrictions. Moving to a slave interface, the R valid output must not combinationally depend on the request input. This means a request shouldn't immediately generate R valid based on receiving a request. There must be some sequential logic. OBI master example. We plan to design an OBI master module for memory built-in self-test or BIST. The module must write the data to the OBI memory, read data from memory, and compare it. It must also report a pass or fail status and total error count. We will use the OBI sim mem from PULP Platform to validate our design. The write operation. We use a finite state machine to implement this module. Let's look at the write operation. During the write request state, the master provides both the address and data. The address itself is calculated as the sum of the base address and the word count. We then left shift this value by 2, which ensures word alignment for our 32-bit data bus. The write data is generated by XORing a test pattern with a word counter to produce a pseudo-random pattern. For this operation, the master must assert its request and write enabled signals. Therefore, when the module is in the write request state, it automatically sets both the write enable and request signals to high. Then the master must wait for the grant from the slave. When the grant signal is high, the master increments the word count and generates the new address and write data. This process repeats until all data has been written to the memory. Afterwards, it transitions to the write wait state. We use this wait state to clearly separate the R valid signal for reads versus writes, which is very helpful for debugging. OBI master read operation. Read operation is similar to write operation. Here the write enable is low and the write data bus is a don't care. Again, when FSM is in the read request state, the request signal is set to high. OBI master simulation results. The simulation waveform is shown here. First, we write some data from the address 1000, and then we read the data. As you can see from the waveform, the write and read data match. The RTL code includes a validation block that automatically checks and validates the transaction. Thank you very much for watching this video.